Let's talk about resistors in series. So let's say that we have an EMF and we have a resistor, resistor. So R1, R2, R3. So current is going to flow like that. Now, the power supply over here doesn't care what it's connected to. So it could be connected to one equivalent resistor over here that draws the same current. Okay. And so if I want to have the same current, the question is, what would that equivalent resistor be? Well, we know that this voltage V1 equals IR1. That voltage V2 equals IR2. That voltage equals IR3. Okay. And so that means that the loop rule tells us the EMF minus IR1 minus IR2 minus IR3 equals 0. So the EMF is we can, R1 plus R2 plus R3. Okay. Now, just doing some algebra there. But if I had this equivalent circuit right here, then the EMF is going to equal IR equivalent. Ohm's law. Well, we just look at these two expressions right here, and it's pretty obvious that the R equivalent is equal to R1 plus R2 plus R3. So for a series set of resistors, then what you see is that the equivalent resistance is the sum of the resistors. Okay. Now notice this is analogous to how capacitors in parallel add. Resistors in series act like capacitors in parallel. Now let's consider, what about parallel resistors? So we have an EMF right here. We have R1, R2, and R3. So we have some total current right here, okay? And the total current, okay, splits up here, and some of it goes here, I1, some goes there, I2, some goes there, I3. Okay, so that means that the total current equals I1 plus I2 plus I3. Now, again, we could replace everything on the right with something here that was one equivalent resistor, so that the current going through there is equal to whatever the original total current was. And so I want to know what equivalent resistor is the same as those three resistors up here in parallel. Well, Ohm's law. V equals IR. So I is the voltage over the resistance. Okay. Now these all have the same voltage. The voltage that the EMF is right there. So these all have that same voltage right there. So that means, again, I could call this V equals IR and say this is V over R. Okay, because you're familiar with that technology. And so what I would do is I would say, okay, so I have that I total equals I1 plus I2 plus I3. So that's going to be V over the equivalent resistance. That's going to be V over R1 plus V over R2 plus V over R3. So in other words, the equivalent resistance here, okay, 1 over R1 plus 1 over R2 plus 1 over R3. So in other words, we could say the equivalent resistance is equal to the sum of 1 over R sub I, okay, to the minus 1. Okay, so in other words, this is how parallel resistors add. Parallel resistors add the way that capacitors add in series. Okay, so it's not that hard. Students sometimes get confused as to how to add things, but resistors and capacitors add in a very similar fashion. The only difference is series resistors they add like parallel capacitors. Parallel resistors, they add like series capacitors. Okay. We've already talked about how capacitors add. So that means that this is how you imagine how resistors add. Now, actually, when I was learning circuits, I learned series and parallel resistors first, and then capacitors later. And so the way I think of it is, I think of parallel capacitors adding like series resistors, and parallel capacitors adding like or parallel capacitors adding like series resistors, and series capacitors adding like parallel resistors is how I think of it. But the thing is, they do add like backwards of each other.